Hi everyone, in this video we are going to discuss this example. Okay, so we have to find a value of this complex integral. This integration we have to solve, and where C is a circle mod Z is equal to 1.5. But the most important thing, we have to find the value of integral with the help of Cauchy's residue theorem. Okay, so let us call the given integral as I. Let us call that integral as I. I is equal to integration over C dz upon z square plus 1 z square minus 4. Okay. So, the most important thing is that given curve C. So, what have they mentioned? C is a circle. So, let us mention the given curve where C is the circle mod Z is equal to 1.5. So, this is a given circle. So, let us draw the circle, but to draw the circle we need to have the center and radius of this circle. So, let us find first center and radius, then we will draw the circle. What will I do? I will compare the given circle with this standard equation. This is standard equation of circle where Z0 is center of circle and R is radius of circle. Okay, so let us compare this equation with that one. So you can easily see only mod Z is there, but actually in equation we have mod Z minus Z0. It means Z0 is 0. That means center of circle is 0. Let us mention. So its center 0, that means 0, 0. So let us talk about radius. If you compare right hand side, so R is equal to 1.5. That means we have a circle with center 0, 0 and radius 1.5. So let us draw the circle. So I am drawing the circle here. Imaginary axis, real axis, getting 1, 2, 3, minus 1, minus 2, minus 3, 1, 2, minus 1, minus 2. Okay. So center is 0, 0 and radius is 1.5. 1.5, that means somewhere here. Okay, so let us draw a circle with center 0, 0, radius 1.5. So we have a circle like this, getting? Okay. So the next important thing is a given function. That means the function is given inside this integral. Okay, so let us call it as f of z. So we have f of z is 1 upon z square plus 1 z square minus 4. So this is a function. Okay. So we have to find the value of that integral with the help of Cauchy's residue theorem. So let us recall the statement of Cauchy's residue theorem, then we will plan how to solve this problem. Okay. The statement of Cauchy's residue theorem is integration over C f of z dz is equal to 2 pi I sum of residues. Okay, 2 pi I sum of residues. That means what we do, we find the singular points of a given function. Singular point means what? A point where function is not analytic. We find those points of this given function and we will check those points are lying inside a circle or outside a circle. If singular point lies outside a circle, no need to worry, no need to calculate anything for that. But if the point lies inside a circle, we need to calculate residue. We find the residue for all such points. We take the sum of all these residues and we take the product with 2 pi I, and that multiplication, that product is nothing but the value of integral. Okay. So here also I will do the same. I will find the singular points of this function. We will check those points are lying inside or outside. If point lies inside, then only we will find the residue. We take the sum of all these residues and we take the product with 2 pi I, and that will be the value of this integration. Okay, so let us start to do. So our first task is to find singular points, that means a point where function is not analytic. In simple language we can say the denominator is 0. But see, the problem is that in a bracket they have given a polynomials of degree 2. So our first task is to find the factors of denominator. Okay, so let us start to do. See, some adjustment need to do. 1 upon z square plus 1 is there. I am writing minus 1 minus minus 1, okay, and z square minus 2 square. So you can easily understand minus minus plus, and 4 is nothing but 2 square, right? Okay. See, this is equal to 1 upon z square. Minus 1 means I square, z square minus 2 square. So I am sure you are familiar with this formula, a square minus b square. Do you know this formula? It is a plus b, a minus b. So this formula is applicable for both the brackets, getting? So let us apply this formula, and we will get 1 upon z plus I, z minus I, z plus 2, z minus 2. Okay, so we found out the factors of denominator. So now you can easily see, if I put z is equal to minus I plus I, 0. That means minus I is giving us 0 at denominator. So it's a singular point. Similarly, I, if I put I minus I, 0. Second bracket will be 0. That means again the denominator is 0. So I is also singular point. Minus 2 will give us this bracket 0. Plus 2 will give us this bracket 0. That means I, minus I, 2 and minus 2, all these are singular points. So we got all singular points. Let me mention here. Then z is equal to I, minus I, 2 and minus 2 are singular points of f of z. So these are singular points of f of z. So the next question is, those points are lying inside or outside a circle. Let us find. Z is equal to I, it is here. Minus I is here. 2 point is here, getting, and minus 2 is here. So see, out of these 4 points, I and minus I are lying inside a circle, and 2 and minus 2 are lying outside a circle. Okay, these 2 points are lying inside, these 2 points are lying outside. It means we have to find residue only at these 2 points, since they are lying inside. No need to find residue for 2 and minus 2. Okay, so let us start to do. See, I should mention here clearly. Here z is equal to plus minus 2 are lying outside, and z is equal to plus minus I are lying inside C. Okay, inside C. So there is no more space to write. Make a screenshot of it, then we will go further. So let us find residue at z is equal to I and minus I. Okay. So now the question is how to find residue. Actually, the definition of residue involves a Lorentz series expansion, but see, it's very hectic task. It's very lengthy task to find a Lorentz series about those points, getting, and then find the residue. But see, if you have a pole, we have very simple formula for calculation of residue. Okay. See, let us check these are poles or not. So z is equal to minus and z is equal to I. So both are simple poles, since they have bracket power 1. So these are simple poles. So we have very simple formula to calculate residue. So let me clearly mention here, z is equal to I and z is equal to minus I are simple poles. Okay, so let us use the formula. So residue of f of z at z is equal to I. Okay, so the formula is limit z tends to I, z minus I f of z. This is formula to calculate residue if the given point I or z naught, whatever, is a simple pole. So fortunately we have got a simple pole, so that's why I am using this simple formula. Limit z tends to I, z minus I. So f of z we need to put here. But see, already we have expressed f of z in this way. So let us write into 1 upon what we have, z plus I, z minus I. Z plus 2, z minus 2 means z square minus 4. So this bracket, okay. So we split this bracket in a form of 2 brackets. It is not required. So that's why I am writing a single bracket here. And for first bracket, I have written this two brackets separately. The reason is we can cancel out one bracket. So let us cancel, okay. So for the remaining part of this function, we need to apply the limit. Apply the limit means what? Simply put z is equal to I everywhere, okay. Let us see what will happen. I plus I square minus 4. So I plus I is 2I and I square is minus 1 minus 4. So it's minus 5, right? So 1 upon 2I minus 5. So it is minus 1 by 10I. So it is minus 1 by 10I. So we got the residue at z is equal to I. Similarly, we have to find residue at z is equal to minus I also, okay. So no more space to write, make a screenshot of it first, then I will go further. So let us find residue at z is equal to minus I. So residue of f of z at z is equal to minus I. It is also a simple fold, that means same formula is applicable, okay. So limit z tends to minus I. Here we had z tends to I. Z minus I, so z minus minus I, that means z plus I f of z. So limit z tends to minus I, z plus I, f of z, same f of z I will use 1 upon z plus I, z minus I, z square minus 4, right. What can we cancel here? Z plus I, z plus I. Cancel out. Okay, so I will apply the limit. That means simply at a place of z I am going to put minus I. So minus I minus I minus I square. But see, we know if you take square of any number, minus sign will get vanish. So it is enough to write I square. Getting the point? Since if you take square, minus sign will go vanish. It will get vanish and you will get simply I square. So this is 1 upon minus 2I. And this is minus 1 minus 4. I square is minus 1. 1 upon minus 2I and minus 5. Minus minus plus, so 1 upon 10I. So we got residue at both singular points which are lying inside a circle. Two singular points 2 and minus 2, they are lying outside a circle. No need to find residue at those points. Okay, so let us apply Cauchy's residue theorem. By Cauchy's residue theorem. Cauchy's residue theorem says integration over C. Let me write first. Value of integration is 2 pi I sum of residues, right? So this is equal to 2 pi I. Our first residue was minus 1 upon 10I. The second is 1 upon 10I. See, both residues are same, just having opposite sign. So if you add, those will get cancelled to each other and you will get 0. So 0 into anything, 0. So the value of this integration is 0. So example is over. Make a screenshot of it. Then we will stop. Thank you. See you in next video.